So in this class we will be formally taking up the topic of hidden Markov models. So let's take formally define what is hidden Markov model and what are the probabilities associated with it. So a hidden Markov model, so an HMM is specified by the following components. The first one is the set of states, that is Q1, Q2 to Qn. So a set of n states. Then we have the transition probability matrix. So A is the transition probability matrix. So I am just writing the elements of A11, A12 dot A n1 dot ANN. So that is a n by n matrix showing the transition between n by n states. So this is a transition probability matrix A. So each Aij represents of moving from state I to state j such that summation on j is equal to 1 to n Aij is equal to 1 for all I. So for j is equal to 1 to n, so that means transition from one state to all the other states is having the probability as summing up to 1. We can have observations O, observation set, that is O1, O2 and OT, and so a sequence of T observations. Then we have the emission probabilities or observation probabilities or observation likelihoods. So we are denoting it by B is equal to small b I O small t, small o small t. So this is again, this is a matrix or sequence of observation likelihoods. So an observation OT being generated from state I. and we can have some initial states and final states. So Q0 is the initial state, Qf is the final state. So start state and end state. Right? So the transition probability matrix is of this kind. We have this matrix. So this is Aij. Right? So at this point, the transition from this is the current state and this is the next state. So this is the current, this is the next one. So it's moving from this state to this state. So this is the probability of that. Similarly, we have emission probabilities or transition probabilities. So these are the states and these are the observations. Alright, so this is represented by again a function. So but we can also represent it with the help of matrix. So B of IoT means ith state is having some kind of observation, right? So each of these BI will produce for a single observation, it will produce some probabilities, and a single state for all the observations will produce some probability, right? And then we have the initial probability distribution, that is the priors. Pi is equal to pi 1, pi 2, pi n, and initial probability distribution over states. So we can have some kind of initial settings that each of these states will have this particular initial probability for starting, right? So pi I is the probability of the Markov chain that will start in state I, right? So some states may also have probability 0, starting probability as 0, right? So what does it mean? It means that if any state is having starting probability 0, it means that the chain cannot start with that value, with that state, right? So we discussed that yesterday also, the rainy and sunny. So the the probability of rainy was 0, so we could always start with sunny, right? And then we can again write QA as a set of accepting states QX comma QY. So while representing the hidden Markov model is actually an extension of finite automata. So a set QA is a subset of Q of legal accepting states. Right? And finally we have the Markov assumption, that is P of Qi given q1 dot q2 dot qi minus 1 is equal to p of qi given qi minus 1. So this is the Markov assumption. Right. Now we can also have some another kind of assumption that the probability of an output observation I depends only on the state that is produced by the observation qi. Right. So any of these observations that are produced by some state, so that observation is only dependent on that state. Right, so it is not dependent on any of the previous states. So again, I am writing it P of OI given QI this is Q1 dot QI, right? So if it is dependent on all other states and other observations as well, O1 dot OI dot OT. So this is written as P of OI given QI. So in that instant of time, the observation produced depends upon, in a particular instant of time, I, the observation over a state depends on solely on the state. So this is called as output assumption. Right, so this is actually the probability table that we have taken, right? So these, with the help of these values, taking this assumption. Right. So what are the problems that can be taken up with the help of this model? Right. So we are having a lot of things here, but the primarily we require this is state transition probabilities and observation probabilities. So we require the transition probability matrix and we require the observation likelihoods, and if we have only this much, then we can do something with the help of something based on hidden Markov models, right? And the rest of the things are just formal definition that may be required, that may not be required, or just we may have some kind of assumptions, like if these priors and initial state, final state, accepting states, so we can have some kind of initial assumption that we can do by ourselves, right? But these the probabilities are generated by the learning from the training data. So what are the different problems? So problem number one is actually the likelihood problem. It's called as the likelihood problem. So it is given an HMM, lambda HMM, now whole settings of HMM, the two probabilities are collectively called as lambda A comma B and an observation sequence capital O. Determine the likelihood of PO given lambda. Right, so we have some settings, some probabilities, transition and emission probabilities of a hidden Markov model, and we are given a set of sequence O. So we need to find what is the probability of that sequence, or what is the likelihood of that sequence. There is slight difference between the likelihood and probability. The problem 2 is decoding. What does it mean? Given an observation sequence capital O and HMM lambda A comma B. That's the same thing. Discover the best hidden state sequence Q. Hidden state sequence Q, right? So I will be just explaining these problems. Let's write the third one. Learning. So given an observation sequence O, right, and a set of states, and the set of states. Learn the HMM parameters A and B. A and B. Right? So what are these problems? Let's try to see them in detail. What are these problems? Let's take this one. So what is this problem? This problem is actually just calculating what is the likelihood of a particular sequence. Right, so it means that I am given some states and I am given some sequence. So here I am not given states, but I am given some sequence. Right, so what does it mean? I have the probability, transition probability matrix A, I have the observation probability matrix B. So these two are given. Right, so this is the transition and this is the observation, right? And then I am given some sequence of observations. So let's take a particular example from the book Jurafsky and Martin. So they have taken the example of the weather hot and cold. So hot and cold is actually the state. Hot and cold are states, but how do we measure the states? So we are not able to measure the states. That's why we are having observations, Right. So yesterday we took the observations for rainy and sunny as the temperature, right? So today they have taken, for today's we will be taking the same example that is given in the book of hot and cold weather can be decided by the observations of number of ice creams sold on that day. Right, so this is pretty humorous kind of example. So number of ice creams sold on that day will decide whether that day was a hot day or cold day. Right, so suppose we are given with a sequence, observation sequence O is, suppose it is hot, hot, cold, hot, hot, cold, right? So what is the probability? Sorry, sir. So this is not the, these are the states actually. Observation will be number of ice creams, right? So number of ice creams is 313. This is the sequence, right? On some day it was 3 ice creams were sold, on some day it was 1 ice cream were sold, and on some day it was 3 ice creams were sold, right? So given these observations, given the HMM, what is the likelihood of this observation? So we need to require probability of 313 given lambda. This has to be calculated, right? The problem here is that we don't know what is the sequence of states. So we will come to this later. Let me explain the next problem. So this is the problem of decoding. The problem of decoding is again simple. We have the same thing. We have the observation sequence. Observation sequence is 313, and we need to know what is the best sequence of states, right? So we need to calculate probability of states given 313. So best probability, that is the probability that is highest, best of this. So there can be lot of probabilities. P of hot, hot, hot given 313, right? So hot for this one, then hot for this one, then hot for this one. There can be more. We can have lot of sequence of states: hot, cold, hot given 313. So what is the best sequence of states, or what sequence of states is having the highest probability for this given observation? So this is called as the decoding. Why it is called as decoding? Because we know the observations and then we decode the states, right? So we may have some kind of greedy approach and or dynamic programming approach here. And what is, let's see, the third one. Third one is the learning of HMM. So the learning of HMM is from the observations, right? So I have lot of observations I observe these 3, 1, 3, and a lot of observations are there, 1, 6, 2, 8, 9. So given a set of observations and a set of states, I do also have states. So these are observations and corresponding states: hot, cold, hot, cold, hot, cold, hot, hot. Right. So I have these. So this can be represented like this. Right. This is again a realization of hidden Markov model, a sequence of hidden Markov model, right? So this is hot, cold, hot. This is 3, 1, 3, and these are the further. So having a lot of sufficient number of sequence of states and observations, we need to calculate what is the probability matrix A and what is the observation matrix B. Right. So whatever we are using in the previous two problems, that has to be generated from this sequence. Right. So we won't be going into this learning part, and let's see if we are able to do this decoding part, but we will be doing this likelihood problem. Right. So let's take up an example, right? So for computing the likelihood, we are given the probability transition matrix, transition probability matrix, and the observation matrix, and we require to calculate the likelihood of. So problem 1, given lambda is equal to a b, p of o given lambda is equal to question mark. Let's take o. Let's take o is equal to 3, 1, 3. Alright. So we don't know here what the hidden sequence of state is. Right. So if we are suppose given the sequence of states, if we are given the sequence of states, then can we calculate it? Suppose corresponding sequence of state is hot, hot, cold, hot, hot, cold. So it means it is a sequence of so suppose I am just making an assumption. So assumption. So this is hot, hot, cold, and 3, 1, 3. So you know now this is pretty simple, right? Why it is simple? We know this probability: 3 given hot, 1 given 3, and 3 given cold from the observation table. So what is the observation table here? The observation table is, suppose we have 3 observations and 2 states: hot, cold, 1, 2, 3. We may have more if required. So this is 1 given hot, this is 1 given hot, this is 1 given cold, right? So these are the observation probabilities, and the transition probability matrix is like this. The previous day is hot and cold, the next day is hot, cold. So this is the current, this is the next, right? So this kind of table is given, and from this table, right, so this is actually the lambda. Given this lambda, we can easily calculate P of O given lambda, comma, sequence of states H, C. Lambda is also given and this is also given, right? So in simple terms, we will not be writing this that lambda is given. We will assume that it's given to us. So we will write P of 3 1 3 given H C. So that is equal to, so initially again we can just multiply these probabilities, right? So we can multiply P of 3 given hot dot P of 1 given hot dot P of 3 given cold. So we can multiply these probabilities, right? Right, so because 3 is only dependent on this, 3 is only dependent on this H, so that we factorize this, we will get these terms. But the problem is that we don't know whether this is the sequence of states or there is another sequence of states. So what we will do is that we are required to compute the probability by actually summing up all the possibilities of states of probability, right? So we will be doing it like this. So since we don't know the states, since we don't know the hidden state sequence, right? So we will do, what is that? We need to compute the probability of 313 by summing over all possible weather sequences, or in general let's write state sequences. Weighted by their probability. Right, so what does it mean? It means that, so before continuing, let's see what is O comma Q, the joint probability. The joint probability can be defined as P of O given Q dot P of Q, right? So P of O given Q is observations P of OI given QI, right? So all these probabilities multiplied together, this one, this P of O given Q, summing of for I is equal to 1 to T or 1 to N, any states we have, multiplied by P of Q is again probability states of states. So what is the probability of states? Pi I is equal to 1 to N QI given QI minus 1, right? So in this way, P of 313 given hot, cold can be calculated as P of hot given hot dot P of cold given hot. So this is, the first one is actually the P of only hot, right? So I am representing it by hot given start, means that this is actually the initial prior probability dot p of hot given hot dot p of cold given hot dot probability of 3 given hot dot probability of 1 given hot dot probability of 3 given cold, right? So we have this one as the O given Q, and the above one is, so we have this is this one and this is this one, right? So this is the combined formula. Right, so using some kind of probability axiom, we can factorize the joint probability. If we are having some joint probability, so we can factorize it in multiple variables. Suppose we have this, we require P of O, okay? So we can factorize it into P of O comma Q and summation on Q. That means if I am having the table of this kind, in general I am having this probability table like this, and I am having these as observations, and these as states. Summation of on Q means we will do summation on this side. So if we do the summation on this side, so this is 1, 2 and 3. So summing these two probabilities will give me the P of O is equal to 1. Summing this probability, okay, summing this will give P of O is equal to 2, right? So in this way we can factorize the joint probability table and calculate the marginal probability. This is called as the marginal probability, the probability of any single row or column, right? So in this way we can factorize, and then we can write this as summation on Q, P of O comma Q is P of O given Q dot P of Q, right? This is P of O. Now let us expand for our example, P of 3, 1, 3, and we are assuming that this is given lambda. We are not writing every time lambda, because we will be doing from the lambda A and B itself. So what is this actually? This is P of 3, 1, 3 is, now you see if we expand in the above form, right? So we can write P of 3, 1, 3 given hot dot P of hot, right, plus P of 3, 1, 3 given some other sequence of states dot P of the same sequence of states. So this is x, 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 x plus P of 3, 1, 3 given y, y, y dot P of y, y, y. So for 3 states we will be having 9 possibilities, right? So we need to calculate this for 9 sequence of states, right? If we have 4 sequence of states, 4 observations, there will be correspondingly 4 sequence of states, and there will be 16 possibilities. Suppose we are having 10 sequence of states, right? So there will be more than 1,000 probability values. So this kind of methodology, by directly using the transition probability table and observation table, is not practically feasible. This direct method not practically feasible, or let me write, not computationally feasible. Is not computationally feasible. So just for only 10 sequence of, I have to do lot of calculations, 1,000 into then each of these calculations per expression, right? So for that we have a dynamic programming based algorithm called as, so solution is dynamic programming based forward algorithm. So this forward algorithm actually starts from one sequence and proceeds to the further sequences by calculating them one by one, so reducing lot of computations. Alright, so similar to forward algorithm, there is a backward algorithm also for doing the same thing. So we won't go into both, but we may study this forward algorithm in the next class, and then we will see if we are able to do the decoding and the learning part, right? So this class ends now.